Welcome back. In the last session, we proved that any integral domain D can be embedded in a field, and we constructed such a field which we called it F sub D. Now, this field is just a particular example of construction known as field of quotients, which we are going to define now. So definition, let D be an integral domain, then a field F is called a quotient field or the field of quotients. The field of quotients of the integral domain D. Of D, if it has a subring, okay, if exists a subring, let's call it a D1 in F, such that the following two conditions hold. First, the integral domain D must be isomorphic to this subring D1, and second, we can express the elements of the field F in terms of D1. That is, for any x in F exist elements A and B in D1, and B is non-zero, such that x equal A B inverse. You remember last time when we defined F sub D, we said that the elements in F sub D are equivalence classes in the form A over B. So this is equivalent to AB inverse in this generalization. Now, first what we are going to prove is that the construction we did for F sub D obeys these two conditions, and therefore F sub D itself qualifies as a field of quotients. So let's do this claim. Okay, F sub D is a field of quotients for D, of course. Okay, so the two conditions, the first one is obvious, since D is isomorphic to D prime. The D prime is a subring which we identified in the last session while constructing F sub D. Then the first condition is satisfied. That is by considering D1 equal D prime. Okay, and as for the second, of course, D prime, just to remind you the definition, is A over B. These are the equivalence classes where A is in D. Now for the second condition, we take any element x in F sub D. Then x equal this equivalence class A over B, of course, where the ordered pair A and B is in S. Remember that S equal D cross D star, where D star is integral domain D excluding 0. Okay, then we have the ordered pair A1 and ordered pairs B1. Both, of course, are in S. Okay, then we can write, in fact, AB as follows. A over B equal A over 1 times a 1 over B. Okay? By the definition of multiplication, these two are equal. And this itself, we can write it as A over 1 times B over 1 inverse. And this is by the definition of multiplicative inverse in F sub D. Now, of course, A over 1 and B over 1 are both elements of D prime, So if we identify A over 1 with A and B over 1 with B, then we can write X as A, B inverse with A and B, of course, in the D prime. Just by understanding that A over 1 and B over 1 are expressed as A and B. And therefore, F sub D is a quotient field for D. The quotient field is also called the field of fractions. The field of fractions of an integral domain. This is also a second term that you will find in some textbooks. Now, so far we have been thinking of D as independent structure not contained in any field, and therefore we constructed the field of quotients independent of D with a subring that is isomorphic to D. But what happens if D is already found to be inside a field? So if we have D here and there is a large field which containing D, so there is a sum field F and F contains D. In such a scenario, what would be the field of fractions or field of quotients of D? Do we still have to construct such a field, or it can already exist within the structure of F? It turns out, by looking at the subfields of F which contains D, that the field of quotients of D must be the smallest one of those subfields that's containing D. And this is going to be the subject of the next theorem, which we will state and prove right now. So we have theorem 4. Theorem 4. So let D be an integral domain and F is a field containing D. Okay. Consider the set F prime. So let's consider this set which contains the elements A, B inverse, A, B inverse, where A and B are in D and B is non-zero. Okay. So we claim the following. Then 1 F prime is the smallest subfield of F containing D. Okay, this is 1. 2 F sub D, the quotient field of F, equal F prime. Okay. Now let's go into the proof. First we need to show that f prime defined this way is in fact a subfield of f. Okay, so proof. First, to show that f prime is a subfield of f, we need first to show that f prime contains at least two elements. So we have 0. This is of course the 0 of D. Okay, this equal 0 times 1 inverse. Okay, and this is contained in f prime. We also have 1, and this is equal 1 times 1 inverse, and this is contained in f prime, and therefore f prime contains at least two elements. Okay, and second, we want to show the subtraction. So we take two elements, so we let x and y be in f prime. Okay, so this implies that x equal AB inverse and y equal CD inverse. Of course, A, B, and C, D are all in D, with B non-zero and D non-zero. Okay, so let's take the difference. So we have x minus y, this equal A, B inverse minus C, D inverse. Okay, and this equal, of course, as we said previously, we will be looking at AB inverse as A over B and CD inverse as C over B. So this is a representation, and the addition and subtractions follows the same rule. So this equal AD minus BC. Okay, AD minus BC all over BD. Okay, and this is equal AD minus BC, of course, into BD inverse, and this is in f prime. Okay, now final step in this subfield test, we must show that x, y inverse is in f prime, provided that of course y is non-zero. Okay, now we defined y as CD inverse, and if y is non-zero, then this means that C is non-zero. So already D inverse is non-zero. Now we have x, y inverse equal AB inverse into C, D inverse, again inverse. Okay, and this equal AB inverse. Of course, we are inside the field, so it is commutative, and the order doesn't matter. So C inverse and D inverse, again inverse, so it's going to be D. So this equal, by rearranging, AD into CB all inverse, and this in F prime. So this implies that F prime is a subfield of F. Okay, now we have to show that F prime is the smallest subfield of F containing D. We only prove that it is a subfield. Okay, so let's first verify that it contains D. So let's take any element A in D. Okay, then we can write this element A as A times 1, which also can be written as A times 1 inverse. But this form of elements, the form of elements in F prime. So this is in F prime, which means A is in F prime, and therefore D is contained in F prime. Okay. Now let's verify that F prime is the smallest subfield containing D. And what this means is that if there is any other subfield, let's say F tilde containing D, then we must have F prime inside F tilde. Okay. Just to visualize this situation, if we have D here, this is D, and we have some F tilde containing D, so this is F tilde, then necessarily we must find F prime here. Okay, so this must be F prime. Okay, and now the proof is easy because if we take any two elements in D, or otherwise if we take some element in F prime and we want to show that this element must be in the F tilde, then any element X here must be in the form AB inverse, where of course A and B are element of D. But B inverse does not have to be an element of D, because D is only an integral domain. It's not necessarily a subfield, and D is viewed just as a subring of F. So we have B inverse must be outside D. Okay, it's not necessarily outside, but it can be outside D. So this means that since F tilde contains D, then AB inverse must be in F tilde, which means that F prime is contained in F tilde. Okay, so let's just put this in formal terms. So let F prime, F tilde be a subfield, okay, of F, such that D is contained in F tilde. Okay. Now let X be an element of F prime. Okay. Then this implies that X equal A B inverse, where A and B are both in the integral domain D, and B is non-zero, right? Now this also implies since D is contained in F tilde, then A and B are both in F tilde. Okay. Now also since F tilde is a subfield of F, then it must contain the inverses of all elements. Then B inverse is in F tilde, and this implies that X which equal AB inverse, this is in the F tilde, which means that F prime is contained in F tilde. Okay, so the situation becomes D is contained in F prime, which is contained in F tilde. Therefore, F prime is the smallest subfield containing the integral domain D. Now comes the interesting part on this theorem. We are going to show that F prime is nothing but the quotient field f sub d. Okay, and to see this is really simple. We just need to picture how f sub d looks in relation to the field f, which contains d. So we have our integral domain d, which is contained inside a large field f. Okay, and within this large field there is a subfield f prime, which contains d. Okay, this is all we have done so far, and f prime of course is the smallest subfield. Now where is f sub d in this picture? F sub d is supposed to be a field somewhere here, and this field contains a subring. Let's call it d prime, and d prime has isomorphism with d. So we have some isomorphism going from d to d prime. Okay, now what are the elements of f sub d? Okay, the elements of f sub d are the elements of the form a over b, which are the equivalence classes, and the elements in d prime are the elements of the form a over 1. Okay, but we said we can identify a over 1 with a, and therefore we can identify a over b with a b inverse. Okay, now where is a and b? A and b are elements of the integral domain d, right? And every element in d has its inverse necessarily in f, because f is a field. So we have b inverse somewhere inside f. Okay, and therefore the product ab inverse must be itself inside f. Okay, and we can in fact define f sub d to be all the elements of the form ab inverse, where a and b is in d with b not equal 0. But this is a definition that looks exactly the same like the definition of f prime, which we already proved that it is a subfield of f containing d, and it is a smallest subfield containing d. So we conclude that f sub d is a subfield of f. So f sub d is in fact can be moved here. So we have here somewhere f sub d. Okay, so this is f sub d, which we moved from here. Okay, and f sub d is the smallest subfield of f containing d. Now we have two smallest subfields of f containing d, f prime and f sub d. So two different smallest things is impossible to have. We cannot have two different smallest prime numbers, or two different the smallest natural number. It has to be always one by the very definition of the word smallest. So we end up with f prime must equal f sub d, and this is the completion of the proof of this theorem. Now this will naturally lead us to think about the case of two integral domains that is isomorphic to each other. What about their respective quotient fields? It turns out it is also isomorphic. So let's have a look at this situation. So we have some integral domain D and another integral domain D prime. Okay, so this is D and this is D prime, and D is isomorphic to D prime. So we have some isomorphism, let's say F. Okay, now D has a quotient field which we will call it F sub D. So we have F sub D here, and we have also a quotient field for D prime, which we will call F sub D prime. So we have F sub D prime. Okay, so it turns out that there is also an isomorphism from F sub D to F sub D prime, and this isomorphism is a unique extension of the isomorphism of D to D prime. So let's put this theorem in formal term and get it proved. Okay, so we move into theorem, and this has to be theorem 5. So theorem 5, let D and D prime be two integral domains. Okay, then any isomorphism from D onto D prime has a unique extension to isomorphism from F sub D to F sub D prime. Okay, and we will explain why this extended isomorphism is unique. Okay, so proof, let F from D to D prime be an isomorphism. Okay, now let A over B be an element in F sub D. Okay, now from this we must have F of A equal some element in D prime. So assume that element is A prime, and F of B must also equal some element in D prime. So let it be B prime. Okay, now define a map G going from F sub D to F sub D prime by the following. Okay, G of A over B, this is the forms of elements in F sub D, the equivalence classes. This equal A prime, okay, into B prime inverse. Okay, we said we can use these two different forms interchangeably. We can use either A over B or AB inverse. So this is an element in F sub D prime. Okay, but this equal from here equal F of A times F of B from here inverse. Okay, now we are already identifying the integral domain D with a subring of F sub D consisting of elements of the form A over 1, where A is in D. right? So if we restrict this function g to only d, okay, by understanding that d is a subring of f sub d. So what we get, we have g restricted to d, okay? So we can only take elements of the form a over 1. So we obtain g of a over 1, which equal f of a into f of 1 inverse, and this equal f of a. This is for every a, and therefore f itself is a restriction of g to the integral domain d, okay? F is g restricted to d, and in other words, g is an extension of f, okay? So now we only need to prove that g is an isomorphism and it is unique, okay? So let's first show that g is a homomorphism, okay? So we have, first we show the addition g of a over b plus c over d, okay? This equal, by the addition formula, g of a d plus bc, this is all over, of course, bd, right? And this equal, from our definition of g, this equal f of ad plus bc into f of bd, and this is, of course, inverse, okay? So this equal, because f is an isomorphism, so it is also a homomorphism, of course. So this equal f of ad plus f of bc into f of b, of course, inverse, into f of d inverse. Of course, it is commutative, so the order does not matter, okay? And this in itself equal f of a into f of d plus f of b into f of c, again f of b inverse, f of d inverse. So when we multiply from here, or when we distribute this multiplication over the addition, we obtain here f of a, then f of d inverse will cancel with f of d inverse, so we have f of a, f of b inverse plus f of c, because f of b will cancel with f of b, so we have f of c, f of d inverse, okay? And this, of course, equal g of a over b plus g of c over d. Now let's check the multiplication. So we have g of a over b dot c over d, okay? This equal, we just use the usual multiplication, so this equal ac over bd, okay? And bear our definition, this equal f of ac times f of bd, of course, all inverse, okay? Now f is an isomorphism, so we can write this as f of A into f of C, okay, and this is into f of B, f of D, all inverse, okay, and this equal f of A, f of C, then f of B inverse, f of D inverse, and we can arrange this as f of A into f of B inverse, then f of C, f of D inverse, okay, and this equal G of A over B times G of C over D. So G is a homomorphism. Now we want to show that it is injective, and therefore we will assume, so we'll show injection. So we assume that G of A over B equal G of C over D, okay? So this implies that f of A into f of B inverse equal f of C into f of D inverse, okay? Now this also means we can just multiply by f of D on both sides and also by f of B on both sides. So this implies that f of A into f of D equal f of C into f of B, okay? And because f is homomorphism, this will imply that f of AD equal f of CB, okay? But f is also injective, so we also obtain from here that AD equal CB, right? And therefore, by just dividing both sides by B and dividing both sides again by D, we obtain A over B equal C over D, which shows that G is injective. So G is injective, okay? Now G is also surjective, and this is easy to see. So G is surjective, and if you look at the definition of G from F sub D to F sub D prime, right? So we define G A over B equal A prime into B prime inverse. And what is A prime and B prime? So in F from D to D prime, for each A, f of A equal A prime and f of B equal B prime. So this is where A prime and B prime comes from. And therefore this equals f of A into f of B inverse, okay? Now to show that it is injective, we need to take one element from here. So we let A prime over B prime be an element of F sub D prime, right? And then we want to find the corresponding element in F sub D. But this implies that A prime and B prime are in D prime, right? And F is a surjective function, so exist A and B in D such that f of A equal A prime and f of b equal p prime. Okay, so this means that we can put g of a, right, over b by this definition is equal a prime into b prime inverse, which is the same as a prime over b prime. Therefore, G is surjective, and this completes the proof that G is isomorphism from f sub d to f sub d prime such that G extends f. So f equal G restricted to D. Now, what if there is another isomorphism G prime from f sub d to f sub d prime, which extends f, so that f equal G restricted to D. In this case, we claim that G prime must equal G, so that the extension is unique. Proof is simple. We take any element in f sub d and apply G prime. So G prime of A over B, we can write it as G prime of, then writing A over B as a product of A over 1 into 1 over B. Okay, this equal G prime A over 1 into B over 1 inverse. Okay, and this equal, of course, G prime of A over 1 into G prime of B over 1 inverse. And the reason we can do this is that G prime is an isomorphism and therefore a homomorphism. Now, A over 1 and B over 1 are elements of D, and we assume that G, F is the restriction of G. F is the restriction of G. So this equal F of A into F of B inverse. Okay, and of course this equal G of A over B according to our definition, which implies that G prime equal G, and therefore there is a unique extension of F to isomorphism from F sub D to F sub D prime, completing the proof of this theorem. This brings us to the conclusion of this session, and in the next session we are going to see some applications and examples of embedding of integral domains and rings in general.